who will talk about optimization-based approach for quantum signal processing and its energy landscape.
Great. Yeah, thank you, Andrews, and thank the organizers for the invitation. It's a great pleasure to give a talk here on the QSP optimization, which is a non-convex optimization problem. So this is a joint work with Yulong Dong, who's a grad student, joint advised by Brigitte and myself. And he's quite unusual in the sense that he's currently a grad student in the chemistry department, and he made his unusual move to the math department and will start his fall. And also Jiasu Wang, who's a grad student in the math department at Berkeley. Also Xiang Meng, who was a visiting undergrad student and will join MIT this fall. So this is the plan. I'm going to talk about the optimization-based algorithms for finding the so-called phase factors. I'm going to introduce what the problem is. I'm going to talk about some newer things, still work in preparation, not on archive yet, the energy landscape result. And if time allows, I'm going to mention briefly a new optimization algorithm based on the matrix product state structure and talk about one open question. So I remember that for me, I have been in the quantum thing only quite recently, and what motivated me to join this direction was really due to the quantum summer cluster that Andrew, Umesh, and others organized in the summer of 2018. I remember Andreas announced this QSVT result on board. I thought it was really interesting. Now, a few months ago, this is a paper came from Electrons group that says this QSVT really offers a grand unification of quantum algorithms. I won't talk much about that. I refer you to the preprint as well as the original paper. It's not, I have to say that honestly, this is not the easiest paper I've read, but it is a very informative one. So this is the definition of quantum signal processing. I think it was a terminology coined by Lin Lin in 2017. So there are actually two parts of it. The first part is scalar representation of a polynomial. Here, px is a polynomial with respect to a single variable x. That's it, defined on -1 to 1. And you want to represent this complex polynomial in this pretty weird way. Here, Z is the poly Z gate, and Wx is this 2x2 matrix. So you compute some a phase rotation times a W, a phase rotation times a W, so on and so forth. And it's each of them is in SU2, 2x2 unitary matrix. You multiply them, it's still in SU2. And for practical reasons, you only focus on the upper left part. So yeah, if this is the first time you see it, this will appear again in the talk. This is what is called quantum signal processing. The value of this very non-traditional, at least to me, representation of polynomials is because once you have such a representation, you can immediately convert this to certain eigenvalue transformations of Hermitian matrices, as well as the singular value transformations of pretty general matrices using this following universal circuit, which is why the name grand unification. So I would say that at this point, if you're still listening, you can do one of the two things. One is you have already known this stuff, then there's nothing for it to do. Or this is really the first time you've seen this, then you can completely forget about what is here because it has nothing to do with the rest of the talk. And you only focus on this scalar problem. So what I'm showing, the reason why I'm showing this slide is just to say there's a very good reason why we care about this very non-traditional polynomial representation problem. So this thing, you don't need to memorize this either. It will appear again and again. Okay, repetition number one. So the goal of the QSP, at least when you represent the real polynomials, can be written as follows. You have a polynomial fx with a single variable x, It's a polynomial of degree d. It has a definite parity. It's either even or odd. And another technical condition we ask the fx to satisfy is that a minus 1 to 1, it should be smaller than 1. When it's equal to 1, there's some weird things happening. So we just say, without loss of generality, it's smaller than 1. So the goal of so-called finding phase factors is the following problem. You want to find phi equal to phi 0, to phi d, which are d plus 1 numbers, so that you multiply, given this phi, which are encoded here and here and here, you multiply these things together. That's we call again W is this matrix. You really don't need to memorize this form. So each of them is 2 by 2 matrix, and on the upper left part, you take that, which is the 1, 1 entry, or in the quantum notation 0, 0. The real part of it is called fx. So really, the first time you see it, it seems overly convoluted, but let me say again that all of these steps are necessary in order to get useful quantum circuit later. So a beautiful part is that for any of this function satisfying this condition seems pretty general, the solution is guaranteed to exist, which means that this, by choosing a proper set of phase factors, you can always encode this f. Once you have this, you can actually use the previous quantum circuit to do Hamiltonian simulation, solve linear systems, and blah, 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 do many things. Okay, so once upon a time, which is 2018, these phase factors were considered to be pretty hard to compute. So this is a paper by Andrew and collaborators on PNAS. So in this appendix, they wrote this, However, this computation, which means computing the phase factors, is difficult in practice. So we can only carry it out for very small instances. Specifically, we found the time required to calculate the angles, the same as phase factors, to be prohibitive if it is larger than 32. It is a natural open problem to give a more practical method to compute these phase factors. And very soon, progresses were made. Virtually at the same time, this was the previous GSLW paper, but also by Ha. In 2018, they proposed algebraic methods to compute, which relies on computing roots of a high-degree polynomial to high precision. With the standard double precision arithmetic, you can probably go to about tens to hundreds of phase factors. You can use variable precision arithmetic implemented at the software level, which is very, very slow, and you can go to larger, like let's say maybe towards going to thousands of phase factors, which is still pretty good compared to the like 32. This is what we announced the last year before the lockdown in the quantum workshop here. And so we developed an optimization-based algorithm. There is no rigorous proof why it works, but in practice, it has been shown to be very robust. It all uses the standard precision arithmetic and can robustly compute more than 10,000 phase factors, which is a polynomial degree, 10,000. Pretty much at the same time, a paper by Chow, Andreas, and collaborators, they proposed the technique. I think that there are more than one technique was presented in this paper. I think the real main idea is really this capitalization, which is based on some small perturbation. Again, there's no rigorous proof why it works. The good news is you can also use standard precision arithmetic to compute a very large number of phase factors. You shouldn't take these numbers to be on their face value. I think probably for both techniques, they can compute much larger number of phase factors. But pretty much this problem is practically solved, right? Compared to what I just showed you before, this is prohibitive for 32. Within 2 years or so, I mean, we can compute 10,000 polynomials. For a long, long time, quantum computers won't be able to carry out such expensive calculations. So at the end, I will also, if I have time, talk about, as I said, a new algorithm based on matrix product state structure, where I actually have some local convergence result from a fixed initial guess. But it will also imply that you can say something much more rigorous for this method. Okay, let me now talk about this optimization-based algorithm, what that is. First of all, if you have a polynomial of degree d, because of a parity constraint, you don't have that many degrees of freedom. It's about d over 2 degrees of freedom, because we're talking about a real polynomial, which means that the polynomial is completely determined by its values sampled on d tilde points. Let's say for numerical stability, we sample them on the Chebyshev map. So close to 1 is pretty dense, and close to 0 is a little sparse. But this is only one choice. And then you can naturally formulate the problem of finding phase factors as a minimization problem, which means that I want to minimize the objective function so that this guy is a polynomial. This guy evaluated on this should be xk, sorry. So evaluated on this k, on this d tilde points, all of them at each of this point is an equal sign, which means it's 0. So you're looking for the f phi to be 0, and phi is this d plus 1 phase vectors. The global minimum, as I said, because of the solution guaranteed to exist, means that phi star must satisfy that f phi star is equal to 0. And notice that there's a dimension mismatch here, which is the f only has d tilde, or d over 2, about d over 2 degrees of freedom, but the number of variables d is much bigger than d tilde, so there's no way that the solution can be unique. Therefore, the first step, important step to make the solution plausibly unique, is so-called the symmetric QSP. By the way, the software is available online if you're interested. So we call that this QSP, you just multiply all those 2x2 matrices, and you end up with this kind of representation. A general QSP quantum signal processing says this Q is a complex polynomial. However, if you're only interested in the real part, without loss of generality, you can restrict the Q to be real. This has the benefit that you can immediately prove the Q is real, then the phase factors can be chosen to be symmetric. In the sense that goes like phi 0, phi 1, da da da, and all the way once it reaches d tilde, and you just do a mirror symmetry and goes to phi 1, phi 0. Then you do a number of variable count. This is exactly matches that in fx. So there's some hope the solution is unique. If you hope so, then later I'm going to show you this is a very far away from that, but at least nominally there's some hope. The modified optimization algorithm then becomes this phi restricted to the symmetric phase factors, and you compute this thing where this g is that the real part of u, the 1 u. Okay, so show you some example how this works. It actually converges very, very fast. This is a PSP representation for 1 over kappa x, which is used to solve linear systems, because if you plug A to in the place of x, this becomes like A inverse. So you're doing the A inverse times B, which allows you to solve linear systems. It's a pretty high degree polynomial, 300, and the condition number kappa is set to 10, and this is a polynomial. At the iteration number 6, you can see that the error is already way below 10 minus 10, and I will not do the same. But let me also show you a movie of this thing. Can you see the movie? I'm not sure.
Yes, we can.
Okay, great. Yeah. So start from the first iteration. You can see it's already pretty good, and really at each iteration you gain an order of magnitude or so, and very quickly you get the convergence. And this behavior is rather generic. And some other applications, such as time quantity simulation, which is your computing QSP representation for cosine tau x and sine tau x, things like that. If you compare with the Han method and the GSFW, I want to describe them here. So the optimization-based method can be one or two other magnitudes faster. And a key reason is because the number of bits that's used. If you restrict the number of bits to be the number of bits in the double precision arithmetic, there's absolutely no way you can get anyone, basically. But if you allow yourself to increase the number of bits, you can see it's pretty crazy. You might need to use 3,000 bits, literally, to factorize these polynomials, and then you can compute them accurately. But the optimization-based method, you always use double precision arithmetic. It works. Similar performance for various other applications as well. So this optimization-based procedure also streamlines the process of finding phase factors because you have at least the two options to do so. Now, what I'm talking about is you're no longer have polynomial, but you only have a smooth function or even non-smooth function, such as 1 over x. You have a smooth function, let's say. Then you have two options. One is to numerically obtain the near best polynomial approximation, for example, Ramy's method, and then you, together with numerical optimization, you can find the phase factors. Or in some cases, you directly do the optimization. That also works. But numerically, what we observe is that the option one seems to be numerically more stable, because it's you're doing a polynomial, the optimization really finds the polynomial. You know that when you reach the global minimum, which is objective function equals to 0, when f is real. So this is what we implement in this QSP pack. So now the method works. Let me talk about some new things, which is this energy landscape. The first we thought, okay, maybe the dimension now matches. There's no local minima, but then that's completely not true. You see the algorithm, if you start from the wrong thing, it gets stuck with local minima all the time. So definitely there are local minima. And then let's say maybe the global minimum is unique, but that's not true either. Already, when you just have two independent symmetric phase factors, which are the cases, for example, just two examples here, if you have an even target function, x squared minus 1/2, or an odd target function here. And the benefit is that you don't have two variables, so you can do a contour plot. And the domain is compact, so you will see the entire energy landscape. There's nothing escaping here. So what you can see is that, so there are actually some symmetry structures, some of them are equivalent, but you definitely see that from -pi to pi, -pi to pi, you will see multiple global minima. So the global minima is not unique, and similar here for the odd function. But this seemingly simple, but there is no local minimum, by the way, when you have only have two phase factors. But as long as you get the degree to be a little bit larger, let's say n equals to 5, you will start to see local minima, and this is one of them. And you kind of like you find the local minima, you diagonalize the Hessian, and the smallest singular eigenvalue of the Hessian is bigger than 0, and the function value is also bigger than 0. So definitely this is local minima, and there are many of those. So it might become completely hopeless. We really thought so for a long time. This is such a nonlinear, non-convex optimization with many global minima, with many local minima. How can you say anything about this problem? Well, it turns out you can actually say something too. The first thing is, the first step is to get some uniqueness result. The uniqueness is the following. Is not the optimization problem I said earlier, where you only know the real part of this polynomial p, but you just given this already complex polynomial p. But here Q is real, as I mentioned before. If you only care about the real part of P, then you can set Q to be real. The blue, highlighted blue part is kind of like for experts, which really highlights the difference from the regular QSP result. So what it says is that if Q is real, then the phase factor, the symmetric phase factor, and this is what a mutual set, is unique. And these conditions is hard to memorize if this is the first time you see it. But once you go through it a number of times, these are actually pretty natural conditions, some degrees and parity and normalization conditions. This normalization one is particularly important. It might look a little bit cryptic, but just remember U is a unitary matrix. It naturally says that P squared, this part, plus 1 minus x squared Q squared equals to 1. So that's it. So it's a very non-trivial constraints on this polynomial P Q. Immediate corollary of this uniqueness result is that there's a one-to-one mapping between the global minimizers. So you don't need to worry about the phase factors anymore. There's a one-to-one mapping between the global minimizers and all the admissible pairs of this polynomial PQ, such that the real parts of P is what you want. So in other words, what you're given is a real polynomial f, then what you really want to do is to find the so-called complementary polynomials. The imaginary parts of P and Q both are real, so that they satisfy all the natural conditions together with this normalization condition. But this seems to be quite a hopeless problem, because just by noting this thing, on the left-hand side is something you know, you can factorize it. On the right-hand side, doesn't even look very much factorizable, because you have this P's and Q's. It seems like it's even hard to figure out whether there are like a finite number of local minima, or they're actually like an infinite number of local minima. So this is really the first thing that we need to do in order to go anywhere. It seemed like there's an infinite number of choices, and in these two papers, they did provide a concrete construction for a class of solutions, but it's not clear whether all those solutions can be constructed in that way. So the first step, what we want to show then, is to show that there are actually a finite number of choices. The key here is to use an important idea raised by the paper by Ha, and to convert this regular polynomials to the Laurent polynomials. That's just recall very simple fact that for any x that is from -1 to 1, and I can always write x to be z plus z inverse divided by 2, where z is this space. So let z just rotate here, and it will just project, the real part is projected to -1 and 1. Then you give me any real polynomial fx, I can just do this substitution, then this becomes f z plus z inverse over 2, and this becomes a Laurent polynomial in this slightly more complicated range, c z inverse. Okay, so so this few lines requires a little bit of calculation, but I'm just going to emphasize the importance of it rather than letting you go over the derivation. The important thing of this factorization, which really takes a few lines, is to say that if you look at this thing on the right-hand side, it really doesn't look factorizable. But on the right, on this, if you write in terms of z and z inverse, this is factorizable. So this this p imaginary is exactly what you want, this p imaginary x, but with this x to z substitution and q here. What this means is on the left-hand side, if you can factorize and find all the roots of this function f in terms of this roots for the this factor z minus r, then this pins down all the roots of the right-hand side, because the right-hand side takes the form of this product. And if all the roots of these Laurent polynomials can be pinned down,
then what it means is all the solutions of the global minimizers must be just some sort of combination of the roots from the F. And there are finite, this immediately means that there's a finite number of global minimizers. So the procedure is a little bit messy, therefore I'm not showing it here. What I just want to say is that if you follow this procedure, you can generalize the results in the GSLW and the hard paper to find all the global minimizers with this procedure. Okay, so this means we have a constructive way, which, however, if you really want to do this, this is only a conceptual procedure. If you really want to do this, you still need to use the variable procedure in arithmetic, or essentially like here we assume there's a like an infinite procedure is used. But nonetheless, it says you have a way to find all the global minimizers of this space vector problem. But another reason I'm not showing all of them is because in practice, what we found is you don't care about most of them. You actually only care about one of them. And this one is a very special one. This is, you will see this a couple of times for the rest of the talk, and which is pi/4 pi/2. It's used in the QSP pack for all the numerical examples. It is robust. So far, for the examples we have tested, it's robust for virtually all real target functions we have tested. What this means is if you plug in this phase factor into the QSP representation, it tells you to represent Px equals to I times the D order Chebyshev, and Q is D-1 order Chebyshev second kind. In particular, this Px is purely imaginary, means that the real part is 0. So this is actually one special solution for the very trivial case, which is fx equals to 0. So sorry about the C, the fx equals to 0. So why this one is particularly important is because we found that there's some very nice properties. Near this solution, the convergence of the optimization is actually much faster, and it has also a larger convergence basis. I'm going to show you first with some numerical results. One thing that I want to say is that before that, one thing I want to say is interesting numerical observation, which is also important, that this f, the infinite norm of f, because it's encoded by unitary, it has to be bounded by 1. But if the infinite norm gets approaches 1, the optimization problem is actually very ill conditioned. It can actually be arbitrarily ill conditioned as this 1 minus eta, this eta goes to 0. And this is shown in a number of cases, Hamiltonian simulation, this eigenstate filtering matrix inversion. They have this universal behavior. When the infinite norm goes to 1, this problem, optimization problem, becomes a very, very ill condition. So for representing real polynomials, it doesn't hurt to just multiply by a small factor in front. Let's say multiply fx by c, so c is smaller than 1. So we always assume the infinite norm is bounded away from 1. Let's say it's about half or something. So now let's study this for any given function. And for example, this guy is a random linear convolution Chebyshev polynomial. I just scale this function towards 0. What would happen? So we just study a few clauses depending on this k goes to infinity, or this small constant 10 to the minus k converges to 0. Where does it converge to? This class 1 converges to the important initial guess I talked about before. The rest of them, they converge pretty much to some other Chebyshev polynomials. One thing you've seen is that this guy really stands out in the sense that when the norm of the infinite norm of f converges to 0, it converges to the initial guess way faster. What it means is that this particular branch, which we call it a maximal solution. The reason why it is called maximal is not shown in this slide. It's for technical reasons. But it's also this branch is generated by a version of this G and R method. So this branch of the maximal solution corresponds to this phi 0, which sort of has the largest convergence basin. So it is much flatter around the solution. So you start from that, it's easier to converge to the local the global minimum. So this is the one thing. You can also ask whether this the convergence is actually faster. This is also true because you start from various of this like initial guesses. You can all kind of converge to different global minima, but around this phi 0, the convergence is almost always the fastest. So theoretically, you can actually show that why this is the case, at least to give a partial answer. And this is the following theorem. Says if you denote this phi star to be the maximal solution corresponding to the phase factors, so that this guy is bounded by 1 to 2, then the two norm of the distance between this phi star and this phi 0, this pi over 4, blah, 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 is just bounded by a constant times the infinity norm. So this is really a striking result in the sense, in particular, it is striking because what doesn't show up in this bound. What doesn't show up is the degree d. So actually, you can, as this infinity norm converges to 0, this guy converges quickly in the two norm independent of d for any f, and this is going to converge the maximal solution branch. Remember, they're exponential, I mean, the combinatorial number of branches, but this particular branch, it will converge to phi 0. And what this also shows, what this implies is that, at least for symmetric phase factors, the so-called capitalization technique is unlikely to be effective. The reason is, what this says is you just add a small perturbation, but a small perturbation only leads to a small perturbation of f only leads to a small perturbation of the phase factor. So while capitalization relies on exactly the opposite. So you can also show that this result, I don't believe is sharp, but nonetheless, it's I think the first result of this kind. That is, if f is bounded by 1 over d or d tilde, which is a d over 2, then not only do you have this bound, but also you can show that the Hessian of the global minimum is bounded by 1. So the optimization problem locally is good. And the key reason for this is that, again, at phi 0, you can compute the Hessian analytically, and the lambda means 2. And this bound is enough to show you that the phase factor is not too far away, and then you still have this omega 1 bound. So this shows that the Hessian is positive definite, which pretty much immediately implies that standard optimization algorithm would converge locally. Okay, so maybe in the final very few minutes, I'll just quickly say something about the what this leads to, which is a matrix product state-based optimization method. I mean, again, this is probably not that obvious the first time you see it, but you see it a couple of times, you will see this QSP actually is a pretty interesting structure because it naturally corresponds to a matrix product state. There's a bunch of 2x2 matrices, and you only care about the 1-1, and exactly what you do with a matrix product state with a bound dimension 2. So a cute idea that we thought about is how about just applying this sweeping algorithms in matrix product state, which corresponds to some coordinate descent method to optimize the phase factors. Just to see how it works. It works. So I mean, the function value takes this thing. It's in the tensor format. Here, the left is a vector, right is a vector. In the middle, you have 2 by 2 matrices. If you're familiar with this graphical notation, it should be pretty clear what this is doing. And W in the middle is a 2 by 2 matrix, and all this face and X, those are the external X. So you just do a contraction, it will allow you to compute one objective function value. You could compute the gradient pretty easily with just some slight injection of structures for this MPS structure, and then you can just do the sweeping. So the cost is about d squared per sweep, and you can choose various sweeping directions, edge to center, center to edge, some loop versions, so on and so forth. So let me report some numerical results. This is for Hamiltonian simulation, and the convergence is very fast. So I mean, with a few number of sweeps, and this is 10 to minus 14. And similarly, if you do it for the matrix inversion problem, and you pretty much 6 iterations here at the machine precision, and this is for a couple of hundreds of phase factors. You can do much larger. You can also prove based on all the preparation so far, but specific to this algorithm, you can also get some convergence proof, which is usually the local convergence takes the form if your initial guess is sufficiently close to the optimal one, then blah, blah, blah. But the natural question is, I mean, how do you get that initial guess? But here, because of all the results that has been shown in all these landscape results, what you can show is something much stronger. What you can show is that you start from phi 0, this is fixed initial guess. Then there exists a constant C, so that if F the infinity norm is bounded by this, then you just converge to the maximal solution, and that's it. And there's this exponential convergence. You kind of should call it linear convergence. I should remark that neither this or this nor this is sharp. And one of the reasons, there are various numerical evidences showing that this is probably not sharp. And one of them is the number of sweeps. If you look at this thing, it's linearly depends on D, but in practice, what we observe is pretty much independent of D. So this theorem would predict the cost will be dq, but the numerical calculation shows the cost is much closer to d squared. Okay, let me just wrap this up with one slide of open question. So this observation was made in our PRA paper, this numerical algorithmic paper. Even with all the understandings of this landscape results, we still feel it's a little bit clueless, but it's such an interesting observation, and I want to share with you here and see whether you have ideas. It's just a decay behavior. So with decay is the following. So recall the connection between the smoothness of a function and the decay of the Fourier coefficients of the function. So this is the duality between the regularity of a function and the decay, or in the Fourier domain. So especially if the function is C infinity, then in the Fourier domain, the Fourier coefficients for the decay is super algebraic. If the function is even analytic, then in the Fourier domain it should decay exponentially. So the similar arguments can be carried out for Chebyshev coefficients as well. But what we didn't expect at all was that there is the corresponding decay behavior for the phase factors. So what I'm showing here on the y-axis is the magnitude, showing for several examples. You can try various other things. The observation is the same thing, that these functions, they are smooth. And the Chebyshev coefficients, they will have a decay, exponential decay, or even super exponential decay. But what we didn't expect at all was the symmetric phase factor, very important. The symmetric phase factor, it very closely follows the decay of the Chebyshev coefficient. We were very excited last year and thought we would like to make a direct connection. But then later we encountered there's so many global minima, so many local minima. I mean, this one, I mean, which solution does this belong to? I mean, we don't even know how to characterize this decay at all. Now, at least we have the language to talk about the problem, although to show the decay, there are important technical roadblocks there. The language to talk about the decay would be the phase factor corresponding to the maximal solution satisfies this decay behavior. So at least we can write down a conjecture now, but still how to do that, we have no idea. And if you're interested, I'll be more than glad to talk about like why technically there's some difficulty. And thank you very much for your attention.
Thank you for a nice talk, Lin. We still have time for a few questions. So if anyone wants to ask something, please write in the chat or speak up.
Hi, folks. And Lin Lin, that was a fantastic talk and really beautiful results. Gosh, you keep on coming up with these one after another. And I'm curious on this last question that you raised, which is very provocative, whether it might be due to a relationship between the algebras of polynomials and the algebras of phase coefficients. So, for example, we can add two polynomials. Does that doesn't imply the phase coefficients add? And I'm curious if you have any intuition about how one might construct what kind of homomorphisms you might have there.
So we thought about using more some more structural results to prove any of those things before we completely failed. So at least that means we have very limited understanding of the structure of this QSP. I think we're really at the tip of the iceberg or something. There must be something profound there, but we don't know. So far, in order to prove the results we know, is pretty much based on brute force computation. That's why I'm not showing you. So it really needs to peel like onions, you peel from one layer to another. But there's a very nice induction that you can show that allows you to prove certain results. But the thing that prevents us from proving such results is because many of those things, other than that one theorem I showed before, is D-independent due to some very dedicated telescoping cancellation. Everything depends on D, which means that if you want to talk about decay, you gotta have some way to talk about the Banach space, to talk about the D goes to infinity case. But everything we have so far is pretty much finite D. When you transform from one norm to another, you lose the square root of D. I mean, to us, it's hopeless. But I think there must be some higher perspectives on this because that allows you to see the structure more clearly, but we're completely clueless right now.
But you do have one D independent result. This last one you showed us.
Yeah, but that,
not enough.
That's the starting point, but at this moment, that's not enough for us to show here.
Thank you.
I have another question. It's very nice. You nicely described this observation that there is at least one solution that you can pinpoint, this maximal solution that you named. Is there any chance that there is some continuous relationship between the polynomial and the maximal solution, or this branches out? Like if you change the polynomial, then this maximal solution just becomes a non-maximal solution, or any structural understanding there?
That I don't know, because as I said, many of these calculations are based on pretty brute force calculation. And this, what happens when you reach towards some branching? At some point, it must be out so that they can converge to there and there. But the quantitative description of those is beyond our achievement. Yeah, and also another thing, observation, maybe you can show as well, which is you can also show that if you define the phase factors to be associated with a non-maximal solution. By the way, since you're definitely an expert, I can say what the maximal solution is. It's basically you select this root of this Laurent polynomials. You select all of them to be inside the unit circle, all of them to be outside unit circle, and that corresponds to the maximal of a certain quantity. Yeah, but you can move some of the some of the roots within and inside and outside the unit circle. You get a non-maximal solution, and you probably will also get a certain local convergence result. And we conjecture that the rate will be slower. We're not sure of that, but maybe square root or some other thing.
All right. Thank you once more for a very nice talk. And I suggest that if anyone has any more questions, then let's take those offline because we are approaching the end of day one. So thank you once again, Lin. And I'm not sure if Umesh, you want to say some concluding words for today, or?
Well, just very quickly, just some, first, thanks to all the speakers for great talks. And secondly, just an announcement that now that we just have word that the mask mandate has been lifted. So anybody who's in person, who can be in person, can actually come to the auditorium tomorrow. And it'll be much easier to both attend and maybe even speak. So there's, assuming all goes well. So look forward to seeing you tomorrow. And thanks, Andras, for chairing the session.